This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 7, Catalysts. So you should have watched the two intro lessons. One was on catalysts. These are my notes. I'm going to go through them rather quickly to make sure that I can get through the entire section. So we talked about what a catalyst is. You might have seen the elephant toothpaste demo. If not, you might want to look that up. It is pretty cool, as you can tell by the eyes on this young man. Gave you that flow chart, which is always very helpful. He talked about an exothermic reaction, and the products have less energy than the reactants, which you already know. And there's a transition state in between. Again, something you already should know. So you have A, B, C, D molecules. There has to be some kind of transition state so that they can change places to A, C, B, D as products. So, he also talked about how this catalysts are in living things such as yeast, and how does that work. So if you take something like H2O2, hydrogen peroxide, it takes a lot of energy. There's a large activation energy, a lot of energy to get up that hill in order to decompose into water and oxygen. However, and then, of course, he talked about what the chemists think is actually happening with that transition state, and how the number of atoms with that iron in the middle is this hemi group. So again, the original reaction has that high activation energy, but then you have this transition state, and if you add a catalyst, what happened to that hill is that it got smaller. So to go from hydrogen peroxide to the water and oxygen doesn't take as much energy. It has this intermediate step. So again, sometimes it creates new intermediates and sometimes it doesn't, so it just depends. So in here we have H2O2. Iodine is a catalyst, and if you notice, the iodide ion is a reactant first and a product in another reaction, so those would cancel out. So the catalyst, or in this case the iodide, is not part of the overall reaction at all. Just like intermediates are also not part of the overall reaction. So here we have made an intermediate with this particular elephant toothpaste reaction. So it's actually formed first. There's actually a new product formed, but then that product is used up again in a different reaction. So again, it is also just canceled out in the overall reaction. So here again is the original reaction. We have reactants yielding products going up that big activation energy, but with our catalyst, in this case, there's two reactions that occur, two steps. But either one of those has, both of those are the energies smaller than the original. So that's what a catalyst does, speeds up that reaction by lowering the activation energy. In lesson 2, he talked about the fact that there are different classes. The three forms he talked about were acid-base, surface, and enzymes. So again, he gave you that nice little flow chart. The acid-base catalyst, he gave you the example in gasoline. The surface, he talked about metals and electrons being delocalized. So again, he went through a nice little presentation, or the example of how this happens, and he went step by step, and he called it adsorption, not adsorbing on the metal, but absorbing on the metal. So there is a little difference between that. And then he talked about how, again, that hydrogen can move around on that metal surface and making more collisions, and it's more successful that way. He talked about the Haber process, and that's a really important process because a lot of industries uses ammonia, and it's a really informational or an important reaction that's been used over the years. And then, of course, the enzyme catalyst that you've known before about the enzymes that are used in your body to break up those sugars to make just glucose and fructose, but which is better for your body. So onto your packet. And in this section, you'll learn how catalysts increase reaction rates, including biological catalysts such as enzymes. So here's a cute analogy as well. So in A, if we're looking up here in A, chemical reaction is like driving over a mountain range. For the reaction to proceed successfully, the reactants travels at the base of the mountain, must climb the energy barrier, the mountain range, before they can become products. So A needs to reach B somehow, right? Reach the far valley. So here's our A. We got to go all the way up this mountain in order to get to B where they want to go. But the reactants must gain energy, usually heat, to reach the transition state or that mountain peak, which is why many reactions will not work unless heated. A catalyst makes this process easier by reducing the energy requirement of the transition state. This is like finding a tunnel or a low pass through the mountains. So here on the bottom we have a tunnel, and woo, all right, so if they can get through the tunnel, they are definitely going to get to that B area where they want to go in that valley a lot quicker. Regardless of how much easier the route is, it cannot alter the overall change in elevation from the starting point to the destination. Similarly, a catalyst cannot change the amount of energy gained or lost. So the overall energy required by an endothermic reaction or released by an exothermic reaction remains the same, regardless of how much the catalyst lowers the energy of the transition state. Catalysts permit reactions to work much faster and at lower temperatures. They make it practical to do reactions that were once unsurmountable. I guess that's that little pun there. So pause, fill in the notes, and then play to hear my words. So the biggest thing you want to remember is a catalyst is added to a reaction to speed it up without actually being part of the reaction. How does it do this? It lowers that activation energy, and it allows reactions to travel down a new path, just like that mountain. So are you going to go over the mountain like an original reaction, or are you going to go through the mountain like a tunnel and have a new pathway? But either way, your starting point and your end point were exactly the same. So again, I mentioned this before, the substance is a reactant first in one of those elementary steps, and then a product in the other. So it's not part of the overall reaction because it gets canceled out. So again, a nice little picture here. You have your original reaction, and then your dotted lines here are the catalyst reaction. We've added a catalyst, so it's not as big of a hill to go up. We've lowered the activation energy. We lowered how much energy is needed to get those reactants to turn into products. So again, here, this is just a bunch of numbers to give you more of an analytical view. So in real life, how does this help us? You can pause the video and read all this, but really what it's happening is we have catalytic converters in our cars, and what happens is if we would let the car run on its own, we would get something like 1800 degrees Celsius coming out, and that's really, really hot. But if we have this catalytic converter in here, we would end up with a more clean combustion gas, and it comes out from 13 to 1500 degrees Celsius. Now you might be saying, oh, whoop-de-doo, 300 degrees Celsius, what's the difference? But that would mean a lot in a car, and again, you know, the other processes that happen as well. So there are two types of catalyst. I don't know if he mentioned homogeneous and heterogeneous. He might have briefly mentioned that. So homogeneous just means that the catalyst would be in the same phase as the reactants. So if our reactants are liquid, the catalyst is liquid. That's all that means. And in a heterogeneous, that means our catalyst would be a different phase. So let's say we have liquid and we would add a solid to that particular reaction. So that would be a heterogeneous catalyst. So example of a homogeneous catalyst are these CFCs that in 1989 were a big deal, and they tried to lower that there were no CFCs anymore in like your hairsprays and things like that, because it is a decomposition. It decomposes the ozone layer. So the CFC problem has basically 4 steps. The CFCs are released and rise to that stratosphere. The sunlight breaks those CFCs down, releases this atomic chlorine, and we know that chlorine gas is very, very toxic. 3, the atomic chlorine destroys the ozone. And 4, the increased ultraviolet rays reach the Earth's surface, raising the risk of skin cancer and other dangerous consequences. So that's what's happening here. So we have our CFCs, goes into our atmosphere, the sunlight's going to break it down, and then comes back and lets the more sunlight or more of those UV rays coming down to Earth. Not too good. So here's an example of a heterogeneous catalyst where we have this metal surface like platinum, and we have these hydrogen atoms. So the hydrogen atoms bond to the surface of this metal catalyst, and it's going to break up the HH bond. And so let's say we have something like C2H4, that also comes down, so that double bond breaks into one in the catalyst. We move some H's around here, and then we go from that double bond to a single bond. And this catalyst kind of helps that process out. So that would be an example of hetero, because we have a solid metal surface, and we have these gases that are being catalyzed. So give it some thought, read the question, pause, and see if your answer is correct. Hopefully that made sense. So in enzymes in the biology, the catalyst or your biology reactions in your body, this would be biochem. So here's an example which you've seen before. Again, you have protein catalyst where again that enzyme has that substrate, they're attracting it, and what happens is it breaks it apart. Makes it a little bit easier for your digestive system. So we want to remember that catalysts will speed up a reaction, and rate increases because it's lowering that activation energy. The rate is independent though of concentration, so you want to remember that a catalyst is just going to speed that up. So why don't you pause the video and see if you can kind of fill in these blanks. I'm just looking for, increasing, decreasing, or maybe no change, and then play the video to see if your chart matches my chart, or at least think about them first before you fill it in. And remember, rate constant is that K. So this should make sense to you. This is a nice summary or a nice recap of what we learned in this chapter. Other things to remember for the exam, and I'm going to be quiet now so you can pause the video, read over it, and hopefully this makes sense. Again, this is just a review or a recap. Some AP multiple choice practice. Again, read. See if you can come up with an answer and a reasoning. Should have gotten D. Pause and read that. Make sure you understand. Oh, I think I went too fast there. Sorry. The answer is E. C. Does that make sense? Hopefully you can figure that out. Again, you are taking away F, and F is an intermediate because it was made first and then used up next. And see you in class.